Sharing the cost of a multicast transmission. Multicast is an internet packet transmission mode that delivers a single packet to multiple receivers. It is accomplished by setting up a shared delivery tree that spans all the receivers. Packets sent down this tree are replicated at branch points so that no more than one copy of each packet traverses each link, because it is far more efficient than traditional unicast transmission, in which packets are sent only to a single destination. Multicast is particularly appropriate for distributing popular real-time content, such as movies, to a large number of receivers. Internet content distribution both provides benefits and incurs costs, which we can model as follows. We assume that there are agents located at various places in the network who would derive some utility from receiving the content, and that a cost is incurred each time the content is transmitted over a network link. The policy question is how these costs and benefits should be distributed. More specifically, which agents should receive the content, and how much should each agent pay. To define the problem more precisely, we consider a user population P residing at a set of network nodes N that are connected by bidirectional network links L. The multicast flow emanates from a source node alpha O in N. Given any set of receivers S which is a subset equals to P, the transmission flows through a multicast tree T of S which is a subset equals to L, rooted at alpha O that spans the nodes at which users in S reside. We make the natural assumption that routing is monotonic, i.e. that S1 is a subset equals to S2, implies that T of S1 is a subset equals to T of S2. Each link little l in capital L has an associated cost C of L which is greater than or equals to 0, that is known by the nodes on each end, and each user I assigns a utility value Ui to receiving the transmission. The total cost C of S of reaching a set S of receivers is given by C of S equals to the summations of C of L, summing for all L in T of S, and the net welfare NW of S of delivering content to this set of receivers is given by NW of S equals to the summations of UI summing for all index I in S minus C of S. A cost-sharing mechanism determines which users receive the multicast transmission and how much each receiver is charged. We let Pi, which is greater than or equals to 0, denote how much user I is charged, and rho I denote whether user I receives the transmission. Rho I equals to 1 if the user receives the multicast transmission, and rho I equals to 0 otherwise. The mechanism M is then a pair of functions M of U equals to rho of U and P of U. It is important to note that both the inputs and the outputs of these functions are distributed throughout the network. That is, each user inputs his UI from his network location, and the outputs rho I of U and Pi of U must be delivered to him at that location. The practicality of deploying the mechanism on the internet depends on the feasibility of computing the functions rho of U and P of U and distributing the results. In our model, it is the agents who are selfish. The routers, represented by tree nodes, links, and other network infrastructural components, are obedient. The cost-sharing algorithm does not know the individual utilities, and so users could lie about them, but once they are reported to the network infrastructure, e.g. by sending them to the nearest router, the algorithms for computing rho of U and P of U can be reliably executed by the network. Thus, our interest here is in network complexity, not computational manipulation. Given the selfish nature of agents, the mechanism should be strategy-proof, i.e. revealing UI truthfully should be a dominant strategy. There are two other desirable features one would want in a cost-sharing mechanism. Budget balance, the sum of the charges SPI covers the total cost of transmitting the content, and efficiency, the total welfare, is maximized. The classic result of Lafont and Green, as reviewed in Chapter 9, implies that no strategy-proof mechanism with cross-linear utilities can achieve both budget balance and efficiency. We therefore consider two separate mechanisms, one that achieves budget balance and one that achieves efficiency. To achieve efficiency, we consider a BCG mechanism called marginal cost MC. Let S wave denote the largest set that maximizes NW of S. This is uniquely defined, and let NW wave equals to NW of S wave. Similarly, NW wave minus I is the maximum value over OS of NW of S minus I. Then, the MC mechanism chooses the receiver set S wave and sets payments PI equals to rho I times UI minus NW wave plus NW wave minus I. For budget balance, we choose the Shapley value SH mechanism. The mechanism shares the cost of each link equally among all the agents downstream of that link, and agent I is downstream of a link L if L is in T of the set of I. To determine which agents receive the transmission, we first start with S equals to P and compute the charges. We then eliminate any agent for which the charge exceeds the agent's utility, i.e. Pi, which is greater than Ui, and recursively prune the receiver set until all agents within the set have utilities greater than or equal to their charge. The cross-monotonic nature of these charges, an agent is never charged less after another agent leaves the receiver set, guarantees that the resulting set is well defined, independent of the other in which agents are eliminated. To see why the ordering does not matter, consider the following. We say that an elimination or pruning is legal if the node to be removed is charged more than its utility. An elimination ordering is legal if each individual pruning is legal. We note that if an agent I is charged more than his utility when the set S of agents remains, then this continues to hold when any subset of S remains, because cross-monotonicity requires that I's charges are at least as great. This means that the concatenation of any two legal elimination orderings is also a legal elimination ordering where we ignore duplicate prunings. For example, if 1573 and 7258 are two legal orderings, then 725813 is also legal, as is 157328. Thus, if any two subsets S and S prime can be arrived at by sequences of legal eliminations, then S intersect S prime can also be arrived at by a sequence of legal eliminations. It is easy to see that both MC and SH are polynomial time computable by centralized algorithms. So the issue is whether it is hard to implement them in a distributed fashion. Certainly, any mechanism can be computed by sending all the valuations to a single node, doing the computation, and then returning the results to each agent. In the worst case, this would require sending omega of the size of p bits over some number of links, which is clearly not desirable. It turns out that we cannot do substantially better than this for the SH mechanism. Theorem 14.1. Any distributed algorithm, deterministic or randomized, that computes the SH multicast cost-sharing mechanism must send omega of the size of p bits over linearly many links in the worst case. By contrast, it is possible to compute MC using only two short messages per link and two simple calculations per node. This is done in two phases. The first, a bottom-up transversal, in which welfare values are computed for each subtree of T of P, and The second, a top-down traversal, in which membership bids row I and cost shares Pi are computed for each I in P. The algorithms are given in figures 14.1 and 14.2. In these figures, V of P denotes the node set of tree T of P. CH of alpha, the set of children of node alpha. RAS of alpha, the set of users resident at node alpha. U to the alpha, the sum of utilities of users in a RAS of alpha. C to the alpha, the cost of the link connecting alpha to its parent in T of P, and T to the alpha of P, the union of the subtree rooted at alpha, and the link connecting alpha to its parent. The reason that this simple two-phase algorithm suffices is that computing the MC cost share Pi does not require a from-scratch computation of NW minus I. Rather, it is enough to compute W to the alpha for every node alpha in V of P during the computation of NW. Suppose that I in RES of beta and that Y of U is the smallest W to the alpha of any node alpha on the path from beta to the root of T of P. If Ui is less than or equals to Y of U, then removing I from the set of potential receivers does not change the set of nodes to which the content is delivered. If Ui is greater than Y of U, then removing I from the set of potential receivers does change the set of nodes, and the resulting difference NW wave minus NW wave minus I is Y of U. The proofs of these facts are left as an exercise for the reader. Theorem 14.2. MC cost sharing requires exactly 2 messages per link. There is an algorithm that computes the cost shares by performing one bottom-up traversal of T of P, followed by one top-down traversal. More information.